In 2022, astronomers made a discovery that didn't get nearly enough attention. They found a black hole. Not billions of light years away, not in some distant galaxy we'll never visit. Right here, in our cosmic backyard. 1,600 light years from Earth, closer than most of the stars you can see with the naked eye tonight. And here's the part that nobody talks about. This one? It was just the first. The one we happened to find. Which means there are probably more, drifting through the same region of space we call home. Dark, silent, invisible. And we don't know where they are. So let's talk about what that actually means. Welcome to Void Atlas. I'm your host, and today we're covering one of the most underreported discoveries in modern astronomy. A discovery that quietly, without much fanfare, changed our picture of what's lurking in the space around us. A black hole. Not the supermassive kind at the center of a galaxy, not something we detected by watching an accretion disk blaze with X-rays from millions of light years away. Something much more subtle, much more ordinary, and much more personal. A stellar mass black hole, the corpse of a dead star, sitting in our own cosmic neighborhood, less than 2,000 light years from the planet you're standing on. Its official designation is Gaia BH1, and its discovery was announced on November 2nd, 2022, in a paper published in the monthly notices of the Royal Astronomical Society. The lead author was Karim El-Badri, an astrophysicist at the Center for Astrophysics at Harvard and Smithsonian, and also at the Max Planck Institute for Astronomy. And what El-Badri and his colleagues found was, in the language of the paper itself, quote, "zero first unambiguous detection in our galaxy." Despite the fact that our galaxy is estimated to contain roughly 100 million stellar mass black holes. Let that sink in. 100 million black holes in the Milky Way. And this was the first one we had ever unambiguously confirmed. Not because of what the black hole itself was doing, but because of what it was doing to the star orbiting it. And the reason we hadn't found any before is not because black holes are rare. It's because black holes are invisible. And in the absence of something that makes them visible, an accretion disk, a companion they're actively consuming, an X-ray source, we have almost no way to see them. Before we go further, let me make sure you understand exactly what Gaia BH1 is. Because the word black hole carries a lot of science fiction baggage that I want to put aside. Gaia BH1 is a stellar mass black hole. It has a mass of approximately 9.6 times the mass of our Sun. That makes it a relatively modest black hole, not a supermassive monster like the ones that power quasars or sit at galactic centers. This is the kind of black hole that forms when a massive star, one with perhaps 20 or more times the mass of our Sun, exhausts its nuclear fuel, collapses inward, and then explodes as a supernova. The core of the star, if it's massive enough, doesn't stop collapsing. It keeps going, past neutron star density, past any known form of matter, into a singularity, a point of infinite density where our physics breaks down. And around that singularity, below a boundary called the event horizon, not even light can escape. For Gaia BH1, with its mass of 9.6 suns, the Schwarzschild radius, the size of the event horizon, is about 28 kilometers. 28. You could drive that on a highway in 20 minutes. Inside that 28-kilometer boundary is an object containing 9.6 times the mass of our Sun. And Gaia BH1 is dormant. It is not actively consuming material. It is not producing X-rays. It is not detectable, not producing X-rays. It is not detectable by any telescope that looks for light of any wavelength. It is simply there, in the dark, doing what black holes do when they have nothing to eat. Nothing. This is the category that Gaia BH1 pioneered, the dormant black hole. Not feeding, not glowing, not emitting anything we can detect directly. The only reason we found it is because of the companion star. Let me tell you about that companion, because the geometry of this system is extraordinary. Gaia BH1 is a binary system. The black hole and a sun-like star are orbiting each other. And when I say sun-like, I mean it precisely. The companion star has a mass of about 0.93 times the mass of our Sun, a radius of about 0.99 solar radii, and a surface temperature of about 5,850 Kelvin. It is, in almost every measurable way, extremely similar to our own Sun. If you were standing on a planet orbiting this star rather than our Sun, you would experience very similar conditions. A similar amount of light, a similar warmth, a similar sky. And this star, this sun-like star, is orbiting a black hole. At approximately the same distance at which Earth orbits our Sun, 1 astronomical unit, give or take. The orbital period is about 185 days. Karim El-Badri described it this way in a press statement. Take the solar system, put a black hole where the Sun is, and the Sun where the Earth is, and you get this system. Read that again. The Sun where the Earth is. A black hole where the Sun is. That is the configuration of Gaia BH1. A sun-like star orbiting a black hole at roughly the distance Earth orbits our Sun. And this entire system is 1,560 light-years from us. And we almost missed it entirely, not because we weren't looking in the right place, but because we were looking for the wrong thing. Here's how Gaia BH1 was actually found. And the method matters, because it tells us a great deal about what else might be out there. The European Space Agency's Gaia spacecraft, launched in December 2013 and operational until 2025, was designed to create the most precise three-dimensional map of our galaxy ever assembled. It tracked the positions and motions of more than 1 billion stars with extraordinary precision. Not just where they are, but how they move over time. The path each star traces across the sky, the tiny wobbles and variations in that path caused by the gravitational influence of whatever is near them. And in June 2022, when Gaia released results from its non-single-star processing, its catalog of binary star systems, astronomers began combing through the data. The catalog contained results for more than 800,000 binary star systems. And buried in there, one system showed something unusual. A star in the constellation Ophiuchus, the Serpent Bearer, was moving in a way that was inconsistent with it being alone. Its motion wobbled. Not randomly, not due to noise in the data, but in a regular, periodic way that indicated it was gravitationally bound to something. Something massive and invisible. El-Badri and his team flagged it as a candidate and got to work. They needed to verify it using ground-based telescopes because Gaia's data alone wasn't definitive enough to rule out other explanations, like the unseen companion being a very dim star rather than a black hole. So they got telescope time, a lot of it. Over 4 months, they made 39 separate observations of the system using 6 different telescopes. The first observation was made in July 2022 using the 6.5-meter Magellan-Baud telescope at Las Campanas Observatory in Chile. That observation immediately suggested that the binary might contain a black hole. From there, El-Badri submitted director's discretionary time proposals, the special observing requests that telescope directors can approve when something urgent and interesting comes up, to several other facilities. The team eventually used the Gemini North Telescope in Hawaii, the Keck 1 telescope in Hawaii, the Magellan Clay Telescope in Chile, and the MPG/ESO telescope, also in Chile. The observations they gathered were of the companion star's radial velocity, how fast it was moving toward or away from us as it orbited the invisible companion. Combined with the astrometric data from Gaia, the star's motion across the plane of the sky, the team could construct a complete picture of the orbit, the mass of the unseen companion, its distance, the orbital period. All of it fell into place. The unseen companion had a mass of roughly 9.6 times that of our Sun. It emitted absolutely no light at any wavelength the team could detect. No X-rays, no radio, no optical, no infrared, no ultraviolet. Nothing. The only other explanation for a dark, massive object in this mass range, other than a black hole, would be a cluster of multiple dim objects. But the team carefully ruled this out. There was no signal from any secondary light source in the system. It was a black hole. The first unambiguously confirmed dormant stellar mass black hole in the Milky Way, and it was sitting less than 1,600 light-years from us. Now, before we go any further, I want to address the obvious question: is this dangerous? The short answer is no. Emphatically no. And I want to explain why clearly, because I think it's important to understand both the genuine significance of this discovery and its genuine lack of threat. Gaia BH1 is 1,600 light-years away. 1 light-year is about 9.5 trillion kilometers. 1,600 light-years is about 15 quadrillion kilometers. This is a distance so vast that even if Gaia BH1 were aimed directly at us, which it isn't, it has no special trajectory toward our solar system. It would take millions of years to arrive. And black holes don't quote 3 things at a distance the way they're often portrayed. A black hole's gravity at a given distance is no stronger than the gravity of any other object with the same mass at that distance. If you replaced our Sun with a black hole of the same mass, Earth's orbit would not change at all. We would simply have no sunlight. Gaia BH1, at its distance of 1,600 light-years, exerts approximately 0 gravitational influence on our solar system. We are in no danger. The astrophysicist Sarah Rastello, who studied Gaia BH1 at the University of Barcelona, put it well in an interview. "We should be super happy that we discovered them, and we can consider them as a friend." A friend. A neighbor. A nearby example of something that is actually extremely common in the galaxy. We just couldn't see them before. So, if it's not dangerous, why does it matter? Why is this discovery significant beyond the novelty of closest black hole ever found? Because of what it implies about what we haven't found yet. Here's the key insight. The Milky Way is estimated to contain about 100 million stellar mass black holes. This estimate comes from our understanding of stellar evolution. How many stars of sufficient mass have lived and died in the galaxy's history, and what fraction of them would have produced black holes? 100 million is a large number, but the Milky Way also contains somewhere between 200 billion and 400 billion stars. So black holes are still a small fraction of the total stellar population. But 100 million is still an enormous number. And before Gaia BH1, astronomers had confirmed only a handful of stellar mass black holes in our galaxy. Not dozens, not hundreds, a handful. Because almost all of them were found through X-ray emission, the signature of a black hole actively consuming material from a companion star. These quote, _6, are dramatic and bright and relatively easy to detect. But they represent only a tiny fraction of the total black hole population. Most black holes are dormant. Most black holes are sitting quietly in the dark, not consuming anything, not producing any light. And now we know that some of them are extremely close to us. The question that immediately arises is, how many dormant black holes are in our cosmic backyard? And the answer, based on the discovery of Gaia BH1, is probably a lot more than we thought. El-Badri and his colleagues noted in their paper that the discovery of Gaia BH1 in Gaia's data release, which covered a small fraction of the eventual complete dataset, implies that dormant black holes in wide binary systems are more common than previously estimated. If Gaia BH1 was found in the early data, more will be found in later releases. Gaia's next major data release, based on 66 months of observations, was expected to contain many more such candidates. And indeed, 2 more were found quickly after Gaia BH1. Gaia BH2, discovered in 2023, is located about 3,800 light-years from Earth in the constellation Centaurus. It has a similar mass to Gaia BH1, about 9 times the mass of the Sun. But its companion is a red giant rather than a main sequence star. And Gaia BH3, announced in 2024, is the biggest one yet. It is located approximately 1,900 light-years from Earth in the constellation Aquila, and it has a mass of about 33 times the mass of our Sun, the most massive stellar mass black hole ever detected in our galaxy. 33 solar masses in a black hole, less than 2,000 light-years away. 3 confirmed dormant stellar mass black holes in the vicinity of our solar system. In just a few years of searching, with an instrument not specifically designed to find them. And the searching is barely half done. What will Gaia's complete data release reveal? What will the next generation of astrometric surveys find when they come online. The Square Kilometer Array, the Vera Rubin Observatory, the Nancy Grace Roman Space Telescope, all of these will add new capabilities to the search for dormant black holes. And the expectation among the astronomers who work on this is that the population of known dormant black holes in our galactic neighborhood is going to grow substantially. Let me now tell you about something I find particularly fascinating about Gaia BH1, the puzzle of how it formed. Because the formation history of this system is genuinely mysterious, and it challenges our current understanding of how binary star systems evolve. Here's the problem. Gaia BH1's black hole has a mass of about 9.6 solar masses. This means the star that collapsed to form it, the progenitor star, must have been even more massive. The minimum mass for a star that produces a stellar mass black hole of this size, according to stellar evolution models, is at least 20 solar masses, possibly significantly more. A star with 20 or more solar masses burns through its fuel at an extraordinary rate. It lives for only a few million years, a tiny fraction of the age of the solar system or the galaxy. And before it dies, it goes through a phase as a supergiant, an enormously puffed-up star that can expand to hundreds of times the Sun's radius. Now here's the problem. If the progenitor star was at least 20 solar masses, and if both the progenitor and the companion Sun-like star formed at the same time from the same gas cloud, then when the progenitor expanded into a supergiant, it would have been enormous. Enormous enough to engulf the companion star entirely. When a star is engulfed by a supergiant companion, what happens is called a common envelope phase. The engulfed star spirals through the supergiant's outer layers, losing orbital energy through friction with the surrounding gas. The usual result is one of two things. Either the two stars merge, or the engulfed star survives but ends up on a much tighter orbit, much closer to the center of the supergiant, due to the orbital energy lost to friction. But Gaia BH1 doesn't look like either of these outcomes. The companion, Sun-like star, apparently survived the common envelope phase, and it's on an orbit much wider than standard models predict for a post-common envelope system. The orbital separation, about 1 astronomical unit, should be much tighter if the companion really did spend time embedded inside the supergiant progenitor. So how did this system form? El-Badri and his team acknowledged in the paper that they don't have a good answer. The system, as they put it, is not easily accommodated by standard binary evolution models. It poses new questions. It requires astronomers to revisit their theoretical models of how binary systems evolve, and, specifically, how companion stars can survive the common envelope phase with such wide orbital separations. One possibility is that the progenitor star was not actually on the same orbit as the companion throughout its life. That at some point, the two stars underwent a gravitational interaction that changed their orbital configuration. Another possibility is that the progenitor didn't go through a standard common envelope phase at all, but instead lost its mass more gradually through stellar winds before the final collapse. Neither of these explanations is fully satisfying, and active research is ongoing. What the puzzle tells us is something important. We don't fully understand how black holes in wide binary systems form. And since we now know these systems are more common than we thought, that gap in our knowledge is significant. The formation of Gaia BH1 is a specific, concrete problem that the discovery has handed to theorists, and solving it will teach us something real about stellar evolution and binary system dynamics. Let me also tell you something about what will happen to Gaia BH1 in the future. Because the future of this system is, in its own way, quite remarkable. Right now, the companion sun-like star and the black hole are orbiting each other at about 1 astronomical unit. The star is in its main sequence, burning hydrogen in its core, just like our sun. It's probably been doing this for several billion years, and has several more billion years to go. But eventually, the companion star will exhaust its core hydrogen and expand into a red giant. A red giant can be enormous. Our sun, when it becomes a red giant about 5 billion years from now, will expand to perhaps 100 times its current size, possibly engulfing Earth. When the companion star in Gaia BH1 expands into a red giant, it will start to lose material to the black hole. At a separation of about 1 astronomical unit, the outer layers of the expanded red giant will begin to overflow what's called the Roche lobe, the region of space around the star within which material is gravitationally bound to the star rather than the black hole. Once the star overflows its Roche lobe, material begins to stream toward the black hole, and Gaia BH1 will wake up. The black hole will begin to accrete material. The infalling gas will form an accretion disk, a swirling, superheated disk of plasma spiraling toward the event horizon. That disk will emit X-rays. It will emit radio waves. It will emit light across the electromagnetic spectrum. The dormant, invisible black hole will become an active, luminous object, an X-ray binary, the kind that astronomers have been studying for decades. This won't happen for a very long time, billions of years. But the physics is straightforward. The dormant black hole of today will eventually become the active black hole of the future, powered by the death of its companion. Now, I've been talking about Gaia BH1 specifically, but I want to zoom out and think about the broader picture. Because Gaia BH1 is not just a single discovery, it's a signal. It's a data point that tells us something about the population of black holes in the galaxy as a whole. If we found one dormant black hole 1,600 light-years away, using data from a survey that wasn't even optimized for finding such objects, what does that imply about the total population? Statistical reasoning tells us that a single detection in a small sample implies a much larger underlying population. The fact that Gaia BH1 was found in the early, incomplete Gaia data, in a survey of around 800,000 binary systems that was itself a fraction of Gaia's eventual output, suggests that there are many, many more to be found. Astronomers have used various statistical methods to estimate the number of wide-orbit dormant black holes in the Milky Way. The estimates range widely, from thousands to potentially millions. But the key insight is this: dormant black holes in wide binary systems appear to be more common than dormant black holes in tight binary systems. more common than the classic X-ray binary configuration that dominated our previous understanding of the black hole population. This is a genuine paradigm shift. Before Gaia BH1, the canonical view of stellar mass black holes in binary systems was that they were in tight orbits, actively accreting, visible as X-ray sources. The discovery of Gaia BH1, followed by Gaia BH2 and Gaia BH3, reveals a different category: wide-orbit dormant black holes, invisible except through the gravitational effect they have on their companions. And this category, it turns out, may be the more common one. The Milky Way is full of dark, quiet objects that we didn't know were there. Some fraction of the stars you see in the night sky are accompanied by black holes we can't see. Some fraction of the star systems in our galaxy contain a dormant black hole doing nothing, saying nothing, drifting quietly through space. That's not a threat, but it is extraordinary. It's a reminder that the universe we can see, the universe of light and brightness and detectable energy, is a small slice of everything that's out there. The dark universe is far larger. And this brings me to a broader point that I think is worth making. The story of Gaia BH1 is not just a story about one black hole near our solar system. It's a story about what happens when we build better instruments and ask better questions. The Gaia satellite was not designed to find black holes. It was designed to map the galaxy, to track the positions and motions of stars with unprecedented precision. And in doing so, it accidentally opened a window onto a population of objects that we had essentially no access to before. This is how science works at its best. Not always by targeting a specific unknown and hunting it down deliberately. Sometimes by building a better eye, pointing it at the sky, and discovering that the sky contains things you didn't know to look for. If you're the kind of person who finds that process, the accidental discovery, the unexpected connection, the instrument designed for one purpose revealing another, genuinely exciting, then you're the kind of person Void Atlas is made for. Subscribe. Every week we go somewhere in the universe where the physics is interesting and the questions are real. And there's always more to find. Now, let me take you back to the beginning of this story, to Kareem El-Badri, sitting with the early Gaia data, looking at this star in Ophiuchus with its strange wobble. He has said in interviews that he had been searching for dormant black holes for 4 years before this discovery. 4 years of looking through data sets, developing methods, checking and rechecking candidates, most of which turned out to be something else. A dim star, a data artifact, an orbiting white dwarf, not a black hole. And then, in the Gaia data, a star that wobbled the right way. Not dramatically, not obviously, just enough. Just the subtle, regular perturbation that a 10 solar mass black hole sitting at 1 astronomical unit would produce on a sun-like companion over a period of 185 days. El-Badri described the moment of realization in an interview. The radial velocity data from Magellan came in, and it was immediately consistent with a black hole companion, not consistent with a dim star, not consistent with a white dwarf. A black hole, sitting 1,600 light-years away in a system so geometrically similar to our own solar system that it makes you pause. What makes a scientist's job meaningful, I think, is not just the finding. It's the realization that the universe is larger and stranger than the previous map indicated. That reality contains categories of things we didn't know existed, or didn't know were common. That our picture of what's out there is, at any given moment, incomplete in ways we can't always anticipate. Gaia BH1 is one of those revelations. Not a discovery that reshapes the fundamental laws of physics. It doesn't do that. But a discovery that reshapes the census, the inventory, the map of what's in our galaxy and how it's distributed. 100 million stellar mass black holes in the Milky Way. We had confirmed a handful, found through X-rays, found through dramatic active accretion. Now we know there's a population of quiet ones, wide-orbit ones, dormant ones, sitting at distances measured in hundreds or thousands of light-years, invisible, waiting to be found by the right instrument, asking the right question. Gaia BH1 is the first one we found. Gaia BH2 and Gaia BH3 followed quickly, and the search is not over. There is almost certainly a dormant black hole closer to us than Gaia BH1. We just haven't found it yet. The mathematics of the black hole population, the density of these objects in our galactic neighborhood, and the fact that Gaia was able to find one at 1600 light-years in its early data, all point toward a significant probability that there are dormant black holes even nearer to us than that, perhaps at 1,000 light-years, perhaps at 500, perhaps closer still. We don't know, because we haven't found them yet. The survey continues. The data continues to come in, and every new data release from Gaia, every new sky survey from the next generation of telescopes will add new candidates. New systems where a star wobbles in a way that requires an invisible, massive companion to explain. The dark universe is being mapped, slowly, painstakingly, one wobbling star at a time. And what the map is showing us is that the neighborhood is more interesting, more crowded with invisible things than we suspected. Gaia BH1, 1,560 light-years from Earth, 9.6 solar masses, Schwarzschild radius, 28 kilometers. A sun-like companion orbiting it at 1 astronomical unit. Dormant, dark, invisible, and found. This is Void Atlas. I'm your host, and this is exactly the kind of story we come here for. A discovery that seems small, one black hole a few thousand light-years away, but carries enormous implications for our understanding of the galaxy, for our understanding of black hole populations, for our understanding of binary star evolution, and for our understanding of how much we still don't know about the space around us. Subscribe to Void Atlas, new deep dives every week. The dark universe is full of things we haven't found yet, and we're going to keep looking. Thank you for being here. Until next time, keep watching the stars, even the ones that wobble unexpectedly, especially those. But let me take you even deeper into what this discovery means for the future of black hole astronomy. Because the story doesn't end with Gaia BH1, BH2, and BH3. It's just beginning. And the tools we're building right now are going to change the picture dramatically. The European Space Agency's Gaia satellite completed its science operations in March 2025 after more than a decade of continuous observation. Over that time, it tracked more than 1 billion stars. Its final data release, Gaia Data Release 4, is expected to contain the most complete catalog of binary star systems ever assembled. And within that catalog, astronomers expect to find dozens, possibly hundreds, of new, dormant black hole candidates. Think about what that means. We currently have 3 confirmed dormant black holes in our galactic neighborhood. The final Gaia catalog could contain dozens more. Each one a specific location in the sky, a specific distance, a specific mass, a specific orbital configuration. Each one a data point in the emerging map of the dark objects in our galaxy. And beyond Gaia, the next generation of ground-based and space-based surveys will push even further. The Vera Rubin Observatory, the Large Synoptic Survey Telescope, is now operational in Chile, imaging the entire southern sky every few nights with an 8.4-meter mirror. It will detect the photometric variability of billions of stars, and within that variability, the subtle signatures of stars being gravitationally perturbed by dark companions. The Nancy Grace Roman Space Telescope, NASA's next major space observatory, will conduct wide-field surveys of the galaxy that will further expand our ability to detect astrometric anomalies, the tiny wobbles in stellar motion that betray the presence of an unseen, massive companion. The Square Kilometre Array, the massive radio telescope network now under construction in South Africa and Australia, will dramatically expand our ability to detect the radio emissions from dormant black holes that may occasionally flare. Brief transient events that happen when a black hole accretes a small amount of material from stellar winds or interstellar gas, producing a short-lived radio signal. These flares are rare, but with the SKA's extraordinary sensitivity, even very faint ones will be detectable. What all of this means is that the census of dormant black holes in our galaxy is going to grow dramatically over the next decade. We are on the cusp of a new era in black hole astronomy, not just detecting the dramatic, actively feeding objects that have dominated our understanding of stellar mass black holes, but systematically mapping the quiet, dormant population that makes up the vast majority of the total. And as that map fills in, we're going to learn things we can't currently anticipate. We'll learn about the distribution of black holes in the galaxy, whether they cluster in certain regions, whether they preferentially orbit stars of certain types, whether there are concentrations of dark objects in stellar associations, or open clusters, or other structures. We'll learn about the mass distribution of dormant black holes, which will tell us about the mass distribution of their progenitor stars, and about the physics of core collapse supernovae. We'll learn about orbital configurations, the range of separations and eccentricities and mass ratios found in dormant black hole binaries, which will constrain our models of how these systems form and evolve. Each new detection is a data point, and data points in sufficient numbers become patterns, and patterns become understanding. Let me tell you about one more aspect of the Gaia BH1 story that I haven't mentioned yet. something that connects this discovery to the broader context of how we find things in astronomy. El-Badri has said in interviews that he spent 4 years searching for dormant black holes before finding Gaia BH1. 4 years. That's not unusual in science. Breakthroughs rarely happen quickly. But what's interesting about those 4 years is what they reveal about the methodology. He was not just pointing a telescope at random patches of sky and hoping to stumble upon a black hole. He was developing and refining a method, a way of identifying candidate systems in large datasets and then following them up with ground-based spectroscopy to measure radial velocities. The method requires a specific kind of data, precise measurements of stellar positions over time, combined with the ability to do targeted follow-up observations of candidates. Gaia provided exactly that data. The astrometric measurements from Gaia's first data releases allowed El-Badri and others to identify stars with anomalous proper motion patterns, patterns that didn't fit a single star moving through space, but fit a star orbiting something else. From those candidates, a subset could be identified as potentially hosting a very dark, massive companion. And from that subset, a small fraction would actually contain a black hole. The pipeline is elegant in its simplicity. Find stars that wobble. Measure how fast they're moving toward and away from us over time. Calculate the mass of whatever is causing the wobble. Rule out every alternative. What's left is a black hole. This is the same basic methodology that Karim El-Badri is now applying with his collaborators to the growing Gaia datasets. And it's the same methodology that the next generation of astrometric surveys will use to push even further. The methodology is established. The tools are improving. The datasets are expanding. And the result, the systematic discovery of dormant black holes in the solar neighborhood, is now inevitable. It's just a question of how many there are, and what we'll find when we know where they all are. I want to take a moment to think about what the discovery of Gaia BH1 tells us about the nature of discovery itself. Because there's something philosophically interesting about the way this black hole was found, not by looking for it directly, but by observing the effect it had on something nearby. This is actually a common pattern in the history of astronomy. Neptune was discovered because Uranus wasn't moving quite the way it should. The existence of dark matter was inferred from galaxy rotation curves, the way stars at the edges of galaxies moved faster than expected. The cosmic microwave background was discovered because a radio antenna had an unexplained noise floor. Gravitational waves were detected because the arms of LIGO were being squeezed and stretched by the passing ripples from a black hole merger a billion light-years away. In each of these cases, the discovery came not from detecting the thing itself, but from detecting its influence, the presence of something invisible, something that doesn't emit, reflect, or interact with light in any way we can easily measure, is revealed by the way it distorts, perturbs, or affects the things around it. Black holes are the ultimate example of this principle. They are literally defined by the impossibility of detecting them directly. Light cannot escape their event horizons, so they emit nothing we can observe. Every method we have for finding black holes is indirect. We find them through the X-rays their accretion disks emit. We find them through the gravitational waves their mergers produce. We find them through the way they warp the paths of light from background stars in gravitational microlensing events. And now we find them through the way they perturb the motion of companion stars over time. Each method reveals a different population. X-ray binaries reveal feeding black holes. Gravitational wave detectors reveal merging black holes. Microlensing reveals isolated black holes drifting through the galaxy. And astrometric surveys, like Gaia, reveal dormant black holes in wide binary systems. And the picture that's emerging from all of these methods together is one of a galaxy absolutely full of black holes. Not concentrated in dramatic, visible sources, not lurking in conspicuous locations, distributed throughout the Milky Way, scattered among the stars, most of them dark and silent and invisible, but present, orbiting sun-like stars at distances comparable to Earth's distance from our sun, drifting alone through the interstellar medium, slowly merging with neutron stars or other black holes, producing gravitational wave signals we can now detect. The Milky Way is a different place than the map we had 10 years ago suggested. The map is being revised. And Gaia BH1 is one of the most important contributions to that revision. There's one more thing I want to say because I think it matters. 1,600 light-years is very close by astronomical standards, but it's still completely beyond any possibility of human visitation in any foreseeable future. The fastest spacecraft we've ever built, the Parker Solar Probe, which, at its closest approach to the Sun, reaches about 700,000 kilometers per hour, would take about 2.5 billion years to travel 1,600 light-years. 2.5 billion years. The current age of the Earth is about 4.5 billion years. So Gaia BH1 is close in the sense that it's in our cosmic neighborhood, within the same arm of our galaxy, visible in principle with our telescopes. But it's not close in the sense that we could visit it, interact with it, or be affected by it in any way. The distance that makes it interesting as an astronomical object is also the distance that makes it completely irrelevant to our immediate situation. But knowing it's there is itself valuable. Not for any practical reason, not because it poses a threat or offers a resource, but because knowledge of the universe we actually inhabit is valuable in itself. Because the map we carry of the cosmos around us affects how we think about our place in it. And because the discovery of Gaia BH1 is a reminder that the universe is not transparent to us, that the dark and invisible parts of it are not empty, just silent, and that the tools we build to listen for those silent things will keep finding new answers to old questions. This is Void Atlas. I'm your host, and today we talked about a black hole 1,600 light-years from Earth, discovered by a spacecraft designed to map the stars, found by a scientist who spent 4 years looking before finding it, and now recognized as the first member of a probably large population of dark, quiet, invisible objects in our galactic neighborhood. Gaia BH1, 9.6 solar masses, 28-kilometer event horizon, dormant, dark, close, and just the beginning. Subscribe to Void Atlas. New deep dives every week. The dark universe has more to show us, and we're only just learning how to see it. I'm your host. Thank you for watching. Until next time, the sky is full of things we haven't found yet. And that is exactly as exciting as it sounds. Actually, I want to go one more place before we close, because there's a dimension of this story that connects Gaia BH1 to one of the deepest puzzles in modern astrophysics. And that puzzle is directly related to how the universe makes black holes in the first place. We've touched on the formation problem, the mystery of how the companion star in Gaia BH1 survived the common envelope phase with its orbital separation intact. But I want to go deeper into what this puzzle tells us about the life and death of massive stars, because I think it's one of the most fascinating unsolved problems in stellar physics. When a star, more than about 20 times the mass of our Sun, reaches the end of its life, it does so with extraordinary violence. The core has been fusing progressively heavier elements, hydrogen to helium, helium to carbon, carbon to oxygen, and so on up the periodic table until the core is made primarily of iron. And iron is a problem. Iron fusion doesn't release energy, it absorbs it. So the moment an iron core forms at the center of a massive star, nuclear burning stops. The heat that had been supporting the core against gravitational collapse disappears, and the core collapses. In fractions of a second, literally, the collapse happens faster than a second. The iron core goes from roughly the size of Earth to roughly the size of a city. The collapse is so rapid that the infalling outer layers of the star bounce off the newly formed dense core, driving a shockwave outward. That shockwave, powered by enormous quantities of neutrinos streaming from the core, blasts the outer layers of the star off into space. This is a core collapse supernova. What remains at the center is a neutron star, or, if the core was massive enough, a black hole. The exact boundary, the maximum core mass that can form a neutron star versus the minimum that forms a black hole, is still an active area of research. But roughly speaking, if the pre-collapse core is above about 3 solar masses, the result is a black hole. Here's the thing, though. Not all massive stars die in dramatic supernova explosions. Some, particularly the most massive ones, may collapse directly to black holes without a visible supernova. The outer layers simply fall inward, following the collapsing core, and the entire star disappears. No explosion, no bright flash. Just a star that was there and then isn't. This kind of event has been observed, or at least its result has been inferred. Astronomers have identified cases where massive stars seem to have simply disappeared, where a star visible in archival images is gone in later observations, with no supernova detected in between. The most famous candidate is a star in the galaxy NGC 6946, observed to disappear in 2015. If confirmed as a direct collapse event, this would be the first observed case of a star vanishing into a black hole without an explosion. For Gaia BH1, the formation history might involve something like this. If the progenitor star, the one that eventually became the black hole, didn't explode in a classical supernova, but instead collapsed more quietly, the energy released during the collapse would have been much smaller. And a smaller energy release during the collapse means a smaller disruption to the companion star's orbit. It's possible that the orbital configuration of Gaia BH1, wider than standard common envelope models predict, is actually a signature of a quiet, direct collapse formation rather than a classical supernova. If this is right, it means Gaia BH1 carries in its orbital properties a record of the death of its predecessor star. The way the binary system is configured today tells us something about the way the progenitor died billions of years ago. The orbital separation, the eccentricity, the mass ratio, all of these encode information about the formation event. This is one of the things that makes dormant black holes in binary systems so scientifically valuable. They are, in a sense, fossils, preserved records of ancient, violent events. The companion star has been orbiting the black hole since the moment the progenitor collapsed. The orbital parameters have been set since that moment, modified only by the subsequent gravitational dynamics of the binary. And by measuring those parameters today, we can read them as history, as a record of what happened billions of years ago when the progenitor died. El-Badri and his colleagues are actively developing theoretical models to explain the formation of Gaia BH1 specifically, and the broader population of wide-orbit dormant black holes generally. This is not idle speculation. It's a rigorous attempt to match the observed properties of the system to physical models of stellar evolution and binary dynamics. And the constraints are tight. The model has to explain the mass of the black hole, the mass of the companion, the orbital separation, and the orbital eccentricity, all simultaneously. The model also has to be consistent with the broader population. If many dormant black holes in wide orbits are found by future surveys, the formation model has to be able to produce them in the right numbers and with the right statistical distribution of properties. This is population-level astrophysics, using individual discoveries as constraints on the physics that generates them. Let me zoom out one more time and place Gaia BH1 in the broadest possible context. Because I think there's something beautiful in the fact that a system so close to us, geometrically similar to our own solar system, with a Sun-like companion star orbiting at roughly Earth-Sun distance, contains one of the most extreme objects in the universe. Our solar system is, by most measures, remarkably ordinary. Our Sun is a middle-mass star, not among the most massive or the least massive. Our planets are arranged in a pattern consistent with the standard models of planetary formation. We are at a typical location in the galactic disk, far from the center and its dramatic active nucleus, far from the dense stellar clusters that fill the galactic bulge. And yet, 1,600 light-years from this ordinary place, there is a system that is, on the outside, also ordinary. A Sun-like star, an orbital period of roughly half a year, a configuration that, if you were approaching it from interstellar space, would look at first glance like just another binary star system. Nothing remarkable, nothing especially dramatic. Until you look more closely, until you notice that one of the stars in the binary isn't emitting any light, that it has a mass of 9.6 suns packed into a radius of 28 kilometers. that crossing its event horizon means the end of any physical process that requires space-time to have a future. The extraordinary is hiding in the ordinary. The dramatic is embedded in the mundane. This is one of the truths that modern astronomy keeps revealing, that the universe we see, the bright and obvious part, is only a fraction of everything that's there. The dark and quiet majority is everywhere, including here, in the space around us. Gaia BH1 is not an anomaly. It is a representative, one of a population, the first data point in a census that is only beginning. And that census is going to tell us something real about the galaxy we live in, about how often stars of different masses die, about how binary systems evolve through the violent deaths of their components, about how common it is for a dormant, invisible, 9-solar mass black hole to be orbiting a sun-like star at a distance comparable to the Earth-Sun separation. Common enough, it turns out, that we found one just 1,600 light-years away, before we'd even finished asking the question properly. This is Void Atlas. I'm your host. Today, we spent time with Gaia BH1, a black hole that turned out to be just around the corner, cosmically speaking. A discovery that was quiet when it happened, that didn't make the same headlines as the image of Messier 87's black hole, or the first detection of gravitational waves, but a discovery that, in its implications, is just as profound, because it tells us that the neighborhood is bigger and stranger than we thought, that the dark, quiet objects scattered through our galaxy are not just in other star systems, not just around other kinds of stars, not just in other parts of the Milky Way. They're here, around stars like our Sun, at distances that are close enough to matter to our understanding of where we are and what's around us. Subscribe to Void Atlas. Come back next week. There is more universe to explore, and the instruments we're building are getting better at seeing the parts of it that were previously invisible. Until next time, keep looking, keep asking. The galaxy is full of things we haven't found yet, and finding them, one wobbling star at a time, is one of the most extraordinary things human beings have ever done. I want to add one final thread to everything we've covered, because there's a question that keeps coming up when people hear about discoveries like Gaia BH1, and it's a perfectly natural question. It's the question I want to answer directly before we finish. Could a dormant black hole sneak up on us? Could one be heading toward our solar system right now? Invisible, undetected, on a collision course we haven't anticipated. The answer requires a bit of nuance, so let me be careful and precise. Black holes do move through the galaxy. Gaia BH1 itself is moving through the Milky Way, as everything in the galaxy is. It orbits the galactic center with its own velocity, shaped by the gravitational potential of the entire galaxy. Over millions and billions of years, its position in the galaxy changes. The question of whether a black hole could approach our solar system is, in principle, yes. Any massive object in the galaxy can, in principle, have a trajectory that brings it near us. The galaxy is a dynamic place. Stars pass within a few light years of our Sun on timescales of tens of millions of years. These close passages can perturb the Oort cloud, sending showers of comets into the inner solar system. They don't threaten Earth's orbit directly because the Sun's gravity keeps the planets firmly in place for any stellar encounter at more than a few light-years distance. A black hole passing within a few light-years of our solar system would be more dramatic than a typical stellar encounter, because black holes can be more massive than typical stars. But the gravitational influence of even a 10 solar mass black hole at a distance of several light-years would be modest in terms of threatening Earth's orbit. It would perturb the Oort cloud significantly, potentially triggering a massive comet shower, but it would not pull Earth from its orbit or destroy the solar system. A truly close encounter, a black hole actually entering our solar system or passing within, say, a few hundred astronomical units, would be more serious. At those distances, the gravitational influence would begin to perturb planetary orbits meaningfully. But such an encounter would be extraordinarily rare. The density of objects in the Milky Way is low enough that the probability of any specific object having such a close encounter in the next billion years is tiny. More importantly, such an encounter would not be undetectable. A black hole moving toward our solar system would be affecting stars along its path as it approached. Those perturbations would be detectable, exactly the kind of astrometric anomaly that Gaia and its successors are designed to find. And the time scale over which a close encounter would develop, thousands to millions of years, is long enough that detection would almost certainly precede any serious gravitational effects. So the short answer is no. Not in any time frame relevant to human civilization. Not in any way that we would be unable to detect with the instruments we're building. Not in a way that would be different in character from the stellar encounters that our solar system has experienced throughout its history. What we don't have is a complete catalog of dark objects in our galactic neighborhood. Gaia BH1 was unknown to us before 2022. BH2 and BH3 were unknown before 2023 and 2024. There are others we haven't found yet. But we haven't found them yet is very different from they pose an undetectable threat. The tools exist. The surveys are ongoing. The dark neighborhood is being mapped. And the result of that mapping, as it progresses, will be not anxiety, but understanding. A more complete picture of the stellar and dark object population within a few thousand light-years of us. A map that includes not just the bright stars we can see, but the quiet, invisible companions many of them carry. A census of the darkness that has always been there, just waiting for us to build instruments sensitive enough to notice. Gaia BH1 is the beginning of that census, one confirmed entry in a catalog that will eventually contain many more. And each new entry is a step toward a fuller, more accurate, more complete picture of the cosmic neighborhood we actually inhabit, not the idealized, simplified one we thought we knew. This is what science does. It replaces comfortable simplifications with accurate complexity. It shows us that the universe is richer and stranger and more interesting than the previous model indicated. And it gives us the tools to understand that strangeness rather than being unsettled by it. 1,600 light-years, 9.6 solar masses, a sun-like companion orbiting at 1 astronomical unit, dormant, dark, and now known. Gaia BH1, the first of many. the beginning of a new chapter in how we see the Milky Way. This is Void Atlas. I'm your host. Thank you for spending this time at the frontier of what we know. The dark universe is not empty. It's full of things we're only now learning to see. And seeing them is one of the great adventures of our time. Subscribe. Come back next week. The next discovery is already out there, waiting for the right instrument to find it. Until then, keep looking up. And remember that sometimes the most extraordinary things are hiding in plain sight, invisible until someone asks exactly the right question.